All right, hey everyone, welcome to the first official Fishbowl, which is a new podcast going out to help flame people and any smoke users. Where it's a collaboration between me and Julik. Hey Julik.
Hello, hello.
This first little episode is going to be all about the Matchbox node, and seeing as Julik is a Matchbox developer, I thought it'd be great if Julik could talk us through how they work and kind of demystify the Matchbox.
Yeah, and I thought I could also give a little bit of theory background as opposed to like saying, okay, you go to that website and you find a number of shaders there and you copy paste them and then pray that they work.
And that's I think that's the most important thing about this is it's hopefully you'll be inspired by watching this to make your own.
Yeah. Should we get started, Joe? I think first I can give you kind of a Blackboard introduction into what shaders actually are and what the Matchbox actually is. And then if we can digest that, then we can probably make a couple of very small little matchboxes to sort of give an idea what they actually do in code. Okay, so let's get started. I'm going to be using Paint as my Blackboard, which is a very traditional way of showing stuff. So let's just grab us a blank canvas and let's start the narrative. So basically, what is a Matchbox? Matchbox is a tool introduced somewhere around like 2 years ago, I think. And what Matchbox actually does, it allows you to pick up OpenGL pixel shaders or fragment shaders, and it allows you to put them into your setups, and it actually executes these shaders on your image. So first, I think I need to give a little introduction into what a pixel shader actually is.
Okay.
We have a pixel shader. It's actually also called a fragment shader because it works on image fragments, and depending on which technology you're using, they're going to be called either pixel shaders or fragment shaders. Basically, first of all, you should probably know what a shader is. If for some reason you don't know what that is, a shader is a set of instructions which tells the computer how to transform a certain piece of information in your 3D scene.
Okay.
So, for example, if you have a Maya scene, then in your Maya scene you're going to have objects which are like a pyramid or a cube or anything else of that nature. And in programs such as Maya or Cinema 4D, you tend to assign shaders to them, to these objects, and these shaders are actually surface shaders. And these surface shaders are usually represented as a kind of a node thingy, which is sort of similar to how we build comps usually. So you will have a shader, and then to that shader you will have connections going in from, say, a diffuse map, and you will have a connection from a specular map, which determines how shiny or reflective your object is going to be, and you maybe will have a connection for say a reflection map, which will allow you to make nice shiny surfaces, and all of that stuff actually gets linked to the surfaces of your objects in your scene, and then gets used as surface shaders. And the surface shader in this case is the set of instructions which is given to the renderer as to how to light and illuminate and color in your surface once it has to be shown on screen. So basically, a shader is a set of instructions.
Now that example you just did, Julik, is that something that could be possible in Smoke? How you were showing spec and
Well, not exactly, because we only can do fragment shaders in Matchbox.
Okay.
And I'm going to explain what the difference is. Like this is a very basic kind of thing that you may be used to from 3D environments, and this is called a surface shader.
Yep.
Then when we're talking about shaders, we're actually talking about a set of a set of instructions, like I said, and these instructions can have different forms. For example, you might have a face shader, which works, for example, per face of a surface. So if you have a cube which is built out a number of quads, then it will process the first face of the quad, and then it will process another face of the quad, and another one of the cube, sorry, and so on. Then you might have vertex shaders, and the vertex shaders process every point of your geometry one by one. So if you have a say a quad hanging somewhere in space, for example, you have a quad which is hanging in your 3D scene, and it has 4 vertices at the edges with the coordinates, say, with the vertices A and B and C and D, for example. Mm-hmm. Then what the vertex shader will do, it's going to get called for each point of that quad, and it can do something to that point. For example, one of the traditional things that vertex shaders do is they convert the geometry given to them from the like world representation and the world coordinates to the camera coordinates. So vertex shaders are used for making projections for rendering and stuff like that. But the most important thing is that basically the vertex shaders are going to process every vertex embedded in your geometry, and this is something that is not available to us in Matchbox. They specifically state that you cannot load your own vertex shaders. But the most important thing, and this is actually simpler to explain with a vertex shader, mm-hmm. is that the vertex shader will process the points piece by piece. So again, if we get back to the example of a quad, yep, which is just hanging in space somewhere, then we might have points A and B and C and D on that quad, and they're going to have coordinates like X, Y, and Z. Okay, and then the B is going to have the coordinates XB and YB, ZB, and so on. Then what's going to happen if we apply a vertex shader to it, more or less, is that every one of these sets of coordinates is going to be given to our vertex shader. So if we finish that drawing real quick, then the shader, which is going to work on vertices, will probably look like this. You're going to have a piece of shader code, and this piece of shader code is going to be designed to process the information about each one of these vertices. So if you look at a very simple vertex shader, you're probably going to see that it takes the values of the vertex passed into it, and then it, for example, applies a transformation matrix to them or does some other simple calculation thing, and that's pretty much it. And for example, if you have you can have a vertex shader that moves stuff around. If you take a vertex shader, which basically you can see a vertex shader as a transformation from one set of point attributes to another, and in that case we only have X, Y, and Z. That is the coordinates of that point in space that we're applying the shader to. Yeah. That is just a transformation to some other set of attributes, or a change of these attributes. And
in terms of because I'm coming from this with a tiny bit of ActionScript experience. Mm-hmm. In terms of a grounding in coding, what would you recommend people know to be able to do this comfortably, or to help them, I guess?
Well, to do this like very comfortably, I would recommend learning a bit of math, because this is what it ultimately comes down to. Yeah. But just in terms of coding, like how to write variables and stuff, some basic ActionScript or JavaScript or PHP or whatever experience is very, very welcome, because you basically have to know what variables are, mm-hmm. and you have to know how to do simple arithmetic at least. And then there is also some stuff related to the variable typing, but I'm gonna explain that later on as we go along. The most important thing to remember is that the shader is a small program which is applied to usually very small components of something big. Like a vertex shader is applied per vertex, and it transforms a set of vertex attributes to another set of vertex attributes. For example, you can have a shader which is going to move this quad in one coordinate by a certain number of points. This is just an example. Like if we want to move every point by a certain amount, then we could just say that in that shader, like a hypothetical, very simple vertex shader, we're going to transform from x, y, and z. We're going to transform to actually the same x, and then the same y, and then z plus 1.
Okay.
And that way we can move the whole quad by a certain amount of units in space. So this is what a vertex shader does.
Which is what we don't have in Smoke right now.
Which is what we don't have. But I found that this is a nice kind of an explanation that of the fact that a shader works per component. So it's not like when you're working with a shader, you can operate on the whole thing of the objects you have, whatever kind of object that might be. But it's actually just a small part of the thing that you wanna adjust or change in your scene.
Okay.
And lastly, we get to the pixel shaders, and the pixel shaders are shaders that work on pixels and pixel fragments. So a pixel shader is a way to process the values of a single pixel. And to better explain that, we can draw a very simple raster of pixels, which is going to represent our image. This is going to be an extremely minimal image, which is going to be 4 by 4 pixels.
So like old Game Boy resolution.
Well, even less than that, I think. And if we number these pixels, then we're going to start at 0. This is something that is handy to remember all the time, that most of the programming related things count from 0 as opposed to counting from 1. So we're going to have in X, this is going to be pixel 0 in X, this is going to be pixel 1 in X, this is going to be pixel 2 and 3. And in Y, the same, this is going to be pixel 0, this is going to be pixel 1 and 2 and 3. Okay, and this is going to be a very simple raster of pixels. And if you look at it from the point of from like the standpoint of elements that you can process, the attributes that these pixels have are actually RGB values. So for example, the pixel at 0, 0 has values of RGB, say, I don't know, 0, 0, and 0. So it's going to be full black.
Okay. Yep.
And then some other pixel is going to have some different value. But the most important thing is that if you have a pixel shader, it's going to be a little piece of code. And what that little piece of code is concerned with, and that's all it does, is it takes one single pixel and it changes its output values. It changes its color and its alpha channel, because we can in the Matchbox shaders and in GLSL shaders we can operate on the alpha output as well. Okay. You following me, Joel?
It's sinking in. Obviously, I'm not a programmer, but it makes sense for me. Yeah.
But the most important thing to realize, and what is not always clear right off the bat, is that you would expect that if you are up to do some kind of a computational processing of images, then you would expect that you have an image as a buffer, like you have access in some form to the whole image, and then you can say draw something from this point to that point, and you can say pick up a point from here and move it over here, for example. And this is not exactly what happens in a pixel shader, because in a pixel shader you can basically grab pieces from your existing image every now and then, but you can only write to one specific pixel that you're processing at the time.
Okay.
And why it's organized this way, it's because it uses the concept called parallel computing. So normally, if you have, imagine that you have a large chunk of things that you need to process. In that case, we have pixels. Normally, the way that would happen in sequential processing is that you would grab, say, this pixel, and you would render it, and then you would write it to some output buffer somewhere. Yeah. And
One at
you're
a time.
One at a time. And once you're
Yep.
done with that, then you would grab the next one. And again, you would render it. And you would write it here. And so on and so forth. Now, what happens instead with those GLSL shaders, since they render on your graphics card, they make use of the fact that a graphics card actually has many processing units. This is why the modern graphics cards, which are in machines like the Flame, usually look something like this. Okay? And also, that's why they produce so much heat. It's because they need a lot of cooling.
Yep.
Okay, but the most important thing is that these cards, they have lots of processing units, and what the OpenGL machinery does for you with those pixel shaders is that it will grab your source image, if you're using one, it will load it into memory, the whole image,
Yep.
onto the onto your VRAM on your graphics card. And then it's going to let every processor on your, or every processing unit on your graphics card will be allowed to render one specific pixel, which allows us to, for example, if we have 4 units which can process at the same time, it allows us to grab this pixel and this pixel and this pixel and this pixel and send them off to processing all at the same time. This is why these shaders can be very, very very fast. It's because you can parallelize them in this fashion. So basically every unit is processing a pixel, and every unit only can write into the pixel that is assigned to it. That's why shaders work in this kind of fashion, that you only get one pixel to operate on at a time.
Is this like CUDA specific, or is it like open to any graphics card?
Well, it's not. Shaders are not CUDA per se, because CUDA concerns itself more with things that do general computing on the GPU.
Yep.
And GLSL shaders, they allow you to do computation on textures. So that's something slightly different. But
so
it's
GPU agnostic, really.
Well, it's more or less GPU agnostic, because you need a certain version of OpenGL support to have pixel shaders, but it's more or less agnostic. Yeah.
Cool.
It's not like you need CUDA for that. But this is also, if you get into writing shaders for, say, RenderMan at some point, then you will have approximately the same situation, that all of these render engines are usually organized in such a way that allows them to render, for example, multiple buckets at a time, so that they can render one bucket on one CPU. Or they're organized in such a way that they can render a scanline separately. For example, the Nuke rendering engine tries to render per scanline, and if it can, it's going to try to parallelize its work into buckets, so that each processor can render its own piece of the image. But for the pixel shaders, they work on separate pixels, so that's their way of doing that in parallel. Okay.
Cool.
So how come that this stuff landed in Flame in the first place? I must say that this is a speculation on my part, sort of. My idea of how that happened is that Flame has been using processing on the graphics card for a long time, even for rendering basic things like transforms, and your action setups were always GPU, etc., etc., etc. So it was the next logical step for them to go into processing textures, which is also why we got stuff like substance textures and substance noise and all of these stylized effects, which have appeared, I think, around version 2012 or so. This all comes from the fact that you can programmatically massage textures that you have loaded onto your graphics card. And then the next step for them was to allow us to load our own shaders to process textures, because everything that flows through your batch pipeline, at one point or another, it gets turned into an OpenGL texture.
Okay. I didn't know that.
Well, it does, and they're doing more and more of that. But this is one of the ways how they made Flame feel very fast. And actually, in the background, that's a funny thing, but I think when you have a Matchbox node,
Mm-hmm.
what they do in terms of OpenGL for your Matchbox shaders to work is that they actually set up a very minimalistic OpenGL scene with an actual quad hanging in front of the camera that your texture gets applied to, so that you can render your pixel shader in that texture.
Okay.
Just a little bit of context that you need around it, but they don't give you any access to that. It's just kind of a framework which picks up your Matchbox shader and compiles it and allows it to execute on the GPU, and then reads back the results that you create with it.
Cool.
Now a little kind of an explanation of how a Matchbox shader is put together and what it actually consists of, because this is something that is not completely clear right off the bat when you look at the documentation. A Matchbox shader usually consists of 3 files. So the first file that you absolutely got to have, and which is the most important one. Sorry, this is a wrong color. So the first file that you're going to have is the so-called .glsl file, which actually contains the body of your shader, that is to say the code that you write for processing your pixels.
Okay.
And which does something useful. So this is kind of a part 1. The second part is the so-called XML sidecar file, or at least that's how they tend to call it. And this is .xml, and actually this file is already Flame specific because it defines the UI controls which are going to be shown in batch or in the standalone Matchbox for this specific shader. If you played with the shaders that you already have in Flame, maybe we can grab a very simple shader just to show sort of the point. That if we go to Connect Effects and we press M, then the Matchbox is going to be here. When we get a choice of shaders, you see all of these shaders have sort of different controls. So for example, if we grab a color noise, then you will see that the color noise has the color noise control title, and it's got a checkbox which says animated or not.
Yep.
If we change it to a different shader which does say a twirl, which in our case ain't gonna be doing much because we have just black image, but when we put up some awesome color bars instead, because we got to be original, right? And then we're gonna see what the twirl actually does, and as you can see, the twirl has completely different controls here. So and each Matchbox shader has its own specific set of controls. And what's important to note is that this XML sidecar file, it actually allows you to specify what kind of controls you're going to be using for your specific shader, because obviously different shaders will need different kinds of UI, and also you might want to use that file to say, for example, I don't want to allow certain values in my UI to go below 1. And I don't want them to allow to go above 500 and stuff like that. And you can also add tooltips to these UI controls to make your shader very, very convenient for others. So this is a little piece of XML code which defines your UI. So this is your UI. This is your shader code, which actually gets executed and compiled. And aside from that, you have the .p file, and the .p file is actually the icon that gets displayed when somebody wants to pull up your Matchbox. And this is actually something that some people are not very familiar with in Flame or Smoke, and I'm going to explain that in a second. And the way it's going to be called is going to be .glsl.p. And P stands for proxy icons. So proxy icons are actually special files in a very kind of antique Flame raster image format, just like PNG or TIFF or anything like that.
Yep.
And previously they were used for loading images. So if you were to load your images without the Media Hub, you were able to generate a very small proxy sequence for all your image sequences to be able to scrub through it in your import interface. And this went away in the new versions because everything gets imported through the Media Hub. But what Flame would do when you were requesting these proxies for your sequences, it would take every image in your, say, network share or in your directory, and it would render a very small proxy file from that, and that's what you would be able to scrub through. So, for example,
is that kind of like the text editor? You know how when you're in text and you're choosing font, you can force proxy, and it'll give you a little, or is that different?
Well, it's something like that, except that they were never generated live. They were sort of pre-rendered all the time.
Okay, all right.
And one of the funny things that you might notice is that if you save a standalone batch setup on Flame, or if you save a standalone action setup on Flame, then it will still save a little icon file next to your actual action setup. So you will have a .action file, which is your scene that you can load, and next to that you're probably going to have a file which is going to be called .action.p. And that .action.p thing, that's the icon that's going to be shown when you try to load that setup in icons mode.
Is that how you generate your .p, or is it something?
That's one of the ways to generate the .p. For example, if you if you grab a blank action node for one reason or another and you want to load it, then here you have this switch which goes from proxies to titles.
So like the old import.
Yeah, exactly, and some of the setups are going to have these proxies, and some won't. For example, when you go in Action, when you go to presets, and when you try to load a preset, then those icons that get shown to you are actually all stored in those .p files. Only you don't see them per se in the interface. But if you go titles, then you just see the names of the setups, and if you go proxies, and it's going to show you a neat grid of those .p files. And having that .p file is actually a very good way to let other people know what your shader is actually doing. So if we go to change shader, what we're actually looking at is this directory on my hard drive. Mm-hmm. And it's actually, instead of showing me a list of names of those shader files, which are stored in that directory, it's showing me those .p files, so I can immediately see, okay, this is a color noise, this is a cross-hatching, etc., etc., etc.
Yeah.
This is actually kind of optional. You don't have to have a .p file per se, but once your shader is actually working, it's very nice for your users to have this kind of a .p file to be able to quickly see what it is that your shader actually does.
Yeah.
So those three files, this one only gets used when. This one only gets used when somebody is browsing for your shader with the setup browser, but these two work in a more interesting way. Once the Flame application is running, I'm just going to draw a Flame application as if it was a Mac OS 9 application in the 90s, something like that, just to piss off everybody. So Flame, okay. Then what happens is this. First of all, it's going to pick up your .glsl file, and it's going to compile it into something that can be run on GPU. Like there is when you cannot just grab the shader code as is and load it onto the GPU. You need to do a little bit of a transformation to it, and that's what Flame actually does. So first it reads your .glsl file, and then it loads it into the application. Then it's going to grab your .xml file, this one, and it's gonna read it and check what kind of UI has to be built for that specific shader, and it's going to load that in. Then what's going to happen is that there are going to be some cross-linking involved between these two files, but the most important thing to understand is that once these two files are loaded, then your shader is going to be built, and all the components will be in place so that you can operate on the shader within the Flame UI.
Okay.
And the way you control it is actually something that you also have to be aware of. How it works is this whole concept of uniforms. And this is, I think, also important to explain. Like I said, we're rendering an actual raster of images, and we render all those pixels at the same time. And the funny thing is that it's kind of a difficult thing in running code on computers if you let the same code operate on different pieces of data while giving it access to the same piece of data at the same time. So, for example, you can have the data for one pixel, which is being processed by the shader at some point. And the shader is doing something to that data, and it's doing, say, a blur. And a blur takes a bit of time. So the shader is kind of stuck here, doing a little bit of computation to that pixel.
Mm-hmm.
At the same time, the different pixel gets loaded onto a different processing unit, and the different processing unit starts running a copy of that code. And it gets stuck somewhere here, say, for some reason. The problem is that if those shaders use some specific piece of data, say here, then they might be out of sync with each other. So as a general rule, there is no shared data storage between those shaders that you can actually write to. That's an important thing to realize. So you cannot say save the value of that pixel while you're processing it and recall the value of that pixel when processing some other pixel. And you cannot have a variable which is shared between different pixels that you can write to. So, for example, it's kind of difficult or also like not very efficient to do something like finding the brightest pixel in your image with a Matchbox shader, because you cannot accumulate values throughout the different runs of your different pixels. And because those chunks of data that you work on have to be isolated from each other, you have something called a uniform. No, that's not green. Is not my favorite color today. So a uniform is actually a piece of data which is read-only for your shader, okay? So because it's read-only and because you cannot change it, this data is actually immune to this kind of concurrent modification problem that you have when you process a lot of things in parallel. So that's why you can use these uniforms, these uniform values on all of your pixels. And uniforms store things like the size of the dimensions of your image. They store the current frame. They store things like the parameters of your effect. So if you're going to have a blur, probably the blur radius is going to be one of your uniforms. And the uniforms are usually defined at the top of your shader code. So normally if you open a shader, you will see a number of statements at the top, which are going to start with the word uniform in lowercase, which specify these shared variables. And these uniforms, those uniform variables, can be cross-linked to your XML UI file. So, for example, if you will have, if you're going to have a simple blur shader, then you're likely to have a. This is very thin. We'll take something like that. Then you will have a uniform, which is going to be called radius. Okay, and then here you will also describe one of the controls in your UI, which is also going to be called radius. And once you do that, when you load the shader, Flame will actually link these two together. So what's going to happen is before rendering a frame, you change the value of that radius in your user interface. Flame is going to store that value in a specific, like kind of a cell in memory where the shader has access to. Then it's going to link this shader to that cell in memory, and then the shader is going to be sent off to the GPU together with the value that you define in the user interface. That's kind of a concept how they implement uniforms.
Okay, that makes sense too, because I was personally a bit confused about the XML, like how those saw each other. So that helps, I think, knowing that
they got to have the same name. So if you have a Matchbox shader which is called the box blur.glsl, then your XML file is going to be called box blur.glsl. Oh, I'm sorry, that's my mistake. It's not going to be called .glsl. I think it's just going to be called .xml. I'm not making new shaders every day.
I thought you were testing me.
Yeah, I must admit I'm not like a graphics programming whiz. I just find it nice to play with, and I thought that like the basic explanation how these things work were a bit lacking. So that's why. And then if you have an icon, then you're going to have a file which is going to be called boxblur.glsl.p. That's basically how you got to name them. But the most important thing is that Flame is going to look for the names of the uniforms in your XML file and for the names of the uniforms in your shader code. And this is how these two are going to be linked together. And this process of grabbing your value from your user interface and storing it in the shader and sending the shader off to the GPU, they basically happen one per frame that gets rendered. That's the mechanics of it. Another thing that I think is important to know is what you cannot do with Matchbox, and this was also kind of a source of confusion for people, because some people expected that, wow, we have Matchbox and we can make like plugins with it and everything. Now, here's what you can and cannot do. Like in Matchbox, you only have access to the current frame in pixel form. So what that means is that you have your raster of images, your raster of pixels, and you can render your specific pixel into that raster. But if you have a sequence of images, then you got absolutely no way to ask Flame to give you something from that frame or from that frame.
So you can't do any temporal operations or anything
you cannot do temporal averaging, you cannot do time warping, you cannot do a compound, you cannot do any of that stuff. And also you cannot do most of the stuff that like general C or C++ program could do. So you cannot, like, these are the things that you don't have access to. So I will put big denials here. You don't have access to the frames except for the current one that you're processing. You also don't have access to the file system. So from a Matchbox shader, you cannot actually say, okay, now let's read some data from disk at location such and such, because I need that to process my image. This will actually not work because you don't have any kind of access to the file system whatsoever, and you don't have much access to the computer memory in general as well. You just have those uniforms. And those uniforms can have a form of very simple values or bundles of values, like 4 floating point numbers or 4 integers or a color pot, for example. But you cannot have a very complicated table in there or some pixel data or whatever. So the general thing is that the only thing that you can process with a shader is the current frame. That's all.
Okay. Where you said it's read-only, you can't bring anything in from the file system. What about if it was something in Flame? Like, could you say load a 3D geo from within a Matchbox, or is that not possible?
No, you wouldn't be able to do that.
Okay.
The only way is you would be able to figure out some way to convert your geometry into an RGB image, and then feed that to Matchbox as a texture. But I think this goes way beyond like the degree of perversion that we allow ourselves generally. I think that's just something that it cannot do. And if you really want to do something like that, or if you want to talk to the network, if you want to talk to some server, say, or I don't know, send an HTTP request, all of that stuff is not available in Matchbox.
Okay.
But on the plus side, since these things run on the GPU, they can be very, very fast, and that's something you can put into some good use. Now, the something to say about the code that you're going to be writing, or that you pretty much will have to write. GLSL is these shaders use the GLSL language, which is the GL shading language. And that shading language, for most intents and purposes, it looks a bit like C. So if you've written any C at some point in time, it will look very familiar to you. It also looks somewhat familiar to JavaScript, but it's got types. But the most important thing, in my opinion, is when you're diving into programming these things for the first time, is to just realize how a standard shader will look and how it does its job. Because if you have scripted some Flash before, you know that you have to grab a movie clip, and you probably need to create a movie clip instance, and you will need to change some coordinates in that, and you sort of learn how these mechanics work.
Yeah.
And pixel shaders, the way they work is that they work by the use of so-called magic variables. I call them magic because, as opposed to calling some kind of function when you're executing a shader, what you actually do is you assign a value to a variable, and you have a number of variables that you can use to pull data in. For example, you have a variable to know which pixel in the raster you're processing. What is the coordinate of the pixel that I'm rendering now? Mm-hmm. This is something that is read-only, and you can only read that, and that's one magic variable. And there is another magic variable that you write to, which contains the values that you're going to be outputting from your shader. So a very simple shader is going to look like this. It's going to have a main function, which is the first function that's going to be called when your shader gets called. It's going to have curly braces. There's going to be some visual junk to the left of it and to the right of it, but we're going to get to it at some point. Then you're going to have a curly brace which opens the function. You're going to have a curly brace that closes that function, and this is the processing body of your shader. Mm-hmm. And what you're going to see in there at some point is the assignment to the magic variable. And since we remember that basically what we do is we transform, not necessarily transform, but we create an RGB value for the current pixel, okay, from our shader. You actually have a value that you assign the RGB or RGBA values to change your output color. So there's literally a variable which is called, say, magic RGB that you assign to, and you assign a triplet of values for example, 0 and 1 for green and 0 for blue. Mm-hmm. And that's how you change your output color. Absolute most of the shaders that you're going to see actually do this at some point, and I'm going to tell you exactly how this magic variable is called. But this is like usually the end result of your operation, because the final destination of your shader code is going to be writing the value of that pixel that you're rendering. That's where it ends. And in between these, you are going to have a number of lines which will be doing things like, for example, picking your input color that you're feeding on one of the Matchbox inputs, doing some transformations to these colors, multiplying them, etc., etc., etc. For example, imagine that we would want to write a shader which does some exposure change.
Okay.
So exposure, okay? Now, we're going to assume that you're working with scene linear images. If you're not, then it's going to be more like the discrete color corrector gain that everybody is used to.
Yep.
So you have the standard transfer function, like so. And then we're going to assume that, well, that's horrible drawing. Imagine that it goes from 0 and 0 to 1 and 1. A standard image transfer function. And if you want to change its exposure, then what you're going to do is you're going to change this transfer function to something like so if you raise its exposure, or if you make the exposure smaller, then you're going to change this transfer function to this, for example, if you want to set your exposure to 0.5. And the way that happens is that, by the way, 1 and 0.5, for someone who's very used to the flame color corrector, this is approximately the same as gain of 100 and gain of 50.
Okay. Okay.
That's about the same thing. But the way that works is that you need some kind of a function. You need some kind of a function which allows you to grab an RGB triplet from your source image, and you want to output the same RGB values, but then R times 0.5, for instance, and then G times 0.5 and B times 0.5. This is how you would implement a very simple gain or exposure adjustment. And this is something you can express quite simply with a Matchbox shader, with a fragment shader, because then you're going to have a shader which is, first you're going to have a variable. Well, not per se a variable, but let's start without the uniform, for instance. The most simple thing is going to be the function called main, again, just like we had it previously, with those braces here, and then a curly brace and such. And then what we're going to need to do first is we're going to need to get these values. And this is kind of a special thing, is that in a Matchbox shader, you don't get those values right away, but you have to sample them. And you have to sample them from your inputs as if there were textures. So you say, dear Matchbox, walk to that texture and sample me the point on that texture at coordinate such and such. So first you're going to retrieve those values from your input, which looks approximately like so. Some input RGB is a sample from your texture at your current X and current Y. And so this is going to be your RGB value. And then you're going to say output RGB, which is that magic variable that we've discussed previously, equals the previous RGB multiplied by 0.5. The way that you have to see it is that it's going to grab every component, and it's going to multiply it by 1.5, which is the way GLSL works with vectors, which I'm going to explain. But this is actually, you can see that just as a triplet of values.
Okay, that makes sense.
So this is what would happen, and obviously this would be cast in stone, sort of preset in your code of your shader, and you would want to have a nice slider in your shader instead. So what you're likely to do is you're going to say, well, this 0.5 value actually has to be a uniform, which I can then reference from my Flame UI. So you're going to say gain, and then somewhere here you're going to say uniform gain. And this will let the shader compiler and this will let Flame know that you actually have a uniform value, which is going to be the same for all the pixels that you're processing. And this value is going to end up being used here for determining your transfer function. So this is sort of what you would have in a color corrector like Matchbox shader. This is what you're likely to do. And also other parameters, for example, if you would want to make some lift, which would work like so. Let's say I want to make it red. Then we want to make some lift. And as we know, lift will lift up our transfer curve by a certain amount, say by 0.4. Okay?
Yep.
Then if we would want to add lift to that mixture, then we would probably say that we actually want our out RGB to be equal to our source RGB multiplied by the gain value, which is going to determine like the slope of our transfer curve for the color correction. So it's going to be times gain, and then plus the lift. And the lift is the same as the offset in the color corrector. Okay, so we're going to need another uniform in that case, which we're going to call lift. Okay, and that's pretty much how it works. So you have a number of uniforms, you have your current pixel that you can write to, you know on which coordinate you are in the raster that you are rendering at the moment, and you are able to reach out to the values of your UI controls, and you are able to sample from your inputs. And this is how all of these GLSL shaders work. Even the smallest one are going to be using this variable, for example, at some point. So, Joel, I'm actually very curious, how much did you actually understand from what I just said?
Yeah, a lot of it makes sense. Obviously, this will be easier to put into practice, which we'll do for the next episode.
Yeah.
It's taken a while to sink in. I like the visual side of it. It's pretty simplified. I guess it's as simplified as it can be. I just had one other thing. You spoke about what Matchbox can't. I know that like what can it do? Like, you know what I mean? Like so like color correctors
in terms of applications. Okay.
Yeah.
That's a very valid question. So imagine that you have a number of operations that you want to do to your batch setup, just using your pipeline. And let's imagine that we have some averaging in time between frames. So you're going to have a number of frames, and you want to compute an average across these frames to remove noise, for example, or do some other filtering operation. You might have a time warp.
Yep.
And you might have drawing a line, for example.
Like Gmask or something?
Yeah, like drawing a Gmask or just drawing a straight line from point to point, or a spline which curves around a little bit.
Yep.
And you might have a color corrector or a lookup table thingy. And you might have a spill suppressor, say.
Yep.
Judging from this drawing, it's actually quite simple to figure out what we will and won't be able to do. Now, temporal averaging, we don't have access to the frames besides the current one, so this one is out.
Yep.
Time warping, we don't have access to the other frames to compute vectors or do any kind of averaging or anything of that nature is out. Now, drawing a line is actually perfectly possible, except that because we render pixel for pixel, we need a little bit of math to actually determine from the pixel that we are rendering whether there's going to be a piece of line on that pixel or not. But we can totally do align. So this one is in. Color corrector, just like we said, this is a perfect use case for a color corrector because we can operate on a pixel at a time.
Yep.
So this is like a completely valid example. And most of the time, the same with the spill suppressor, except that you might want to have some kind of a very smart spill suppressor that registers temporal change in color. That ain't gonna fly, but most of the spill suppressors will be possible.
Okay.
So this is an example, and also all the things which have to do with image filtering, like blurs and noises and stuff like that. This stuff is usually very well doable with pixel shaders. I think I'll add that especially because one of the things that we're going to be doing as our endeavor is we're going to be writing a very simple blur in Matchbox just to show how you kind of manage your iteration through your pixel values. Let's take a break and then let's do part 2.
Cool.